fun, y'all. Have fun, y'all. City breathing all down your neck. Bad news and good dope special effects. And reality's teeth, bright, black, sinking in deep. Ow. Who ain't shy of the pain? Who ain't shy of the pleasure, just the same? Life is a game, I heard the homies say. Well, I came to win, so I'm not here to play. Have fun, get it, get it, get it, get it, get it, get it, get it. Hey, get it, get it. Yo, don't stop. Ecstatic, fantastic, get it, wow, get it, wow, get it. People. Bad news and good dope, powder, potion, pill, smoke. Baby, how you trying to go? Do it or dulce, fast or slow? Yay, no, it's okay, you can have it your way. Nah, it ain't all good, but baby, I'm cool. Feeling great, feeling good, how are you? 10% condition, 90% response. Survival mathematics, the number man song. Old dad dropped the jewels so pure. When the times get raw, it's something I recall. Sometime I don't remember it at all. And I get stormed by the weather, but no umbrella. Sky release pressure and the ground get wetter. My outfit effed up, I could've looked fresher. But guess what? The hell with parade day rain. Tsunami of sunshine, the bomb is just the same. Life is a game, I heard the homies say, but I came to win. Dante, get it, play, get it, get it. Brooklyn, get it. Ecstatic, A-Day, Speedball. Bad news and good dope, powder, potion, pill, smoke. Baby, how you trying to go? Do it or dulce, fast or slow? Yay, no, it's okay, you can have it your way. Nah, now's the time, but baby, I'm cool. Feeling great, feeling good, feeling good, feeling good, feeling good, feeling good, feeling good. Every day, every day, having a good time, every day. Having a good time every day. Having a good time every day. That's cool.
Okay, so last week we introduced this notion of trees, which are a very special type of graph. Remember that we went through and talked about what a graph is, that you've got these nodes, and that each pair of node may or may not be connected by edges. The orientation is one way, or is both ways, that is, it's undirected. A to B is the same thing as B to A. We're only going to consider paths, like routes through the graph, or cycles, one that ends up back where it started, that are simple. We're not going to go traversing back and forth, wasting time, because again, we're trying to have an efficient data structure here. The length of a path is the number of edges on it, and a single edge is of length 1, etc. We made a couple of observations here that a tree is a connected simple graph with no cycles. So it's an acyclic graph. That means that it has exactly n-1 edges, so very, very highly regular if you've got n vertices or nodes. And that between any two nodes there is exactly one and only one path. There's only one way to get from A to B, right? For any A and B in the entire graph. What we want to do now is we want to add some more orientation. This is more for visual purposes, so that we can, because we're going to be reading, we're going to be storing data in it, and we're going to want to read it top to bottom, left to right. So we're going to take, like I said, we can take any one of those nodes out of the screen, dangle it, and then let gravity take over. And it's going to be oriented top to bottom, left to right. The top is the root of the tree, right? The bottom, or the nodes may have parents or children, right? And then we can also use, siblings, ancestors, descendants, right? All that nomenclature that you would use if it were a family tree, you can use in a data tree or a data structure tree, right? A node with no children is a leaf, right? So let's come over here, and here is a tree, right? Again, way at the top here, what we have is called a root, right? Our trees grow downward, right? Why? Because again, we like to store data in it, and we're going to read it top to bottom, left to right. This is how Cayley did it 150 years ago when he introduced this notion. So what do we have as far as leaves? Let me go ahead and change this to green, right? Why? Because leaves are green, right? And so every one that I'm highlighting here is a leaf node, right? These are all leaf nodes. Leaf nodes. Why? Because there are no children, right? P and Q, they have no children below them. C is not a leaf node because it does have a child here, F. Now, if I were to grab C and pull it out of the screen and then dangle it again, that would become my new root node. And so it would change the orientation, it would change the topology of this tree. But we're going to go ahead and fix the topology and then start talking about it, okay? What about these other ones? Let's go ahead and highlight them in another color here. That color, there we go. What about this one, this one, this one, this one, this one? All of the other ones that are not roots, that are not leaves. Sometimes we refer to these as internal nodes. Right? So you've got the root at the top, you've got internal nodes until you get finally up to the tree here, up to the leaves. And so I was coloring them in my closest approximation to brown because, branches are brown, right? And so they are internal nodes. A leaf with no children is a leaf. Otherwise, all other nodes are internal nodes, okay? Again, this induces a parent-child relationship. I'm going to add more structure. We will limit the number of children to at most 2. Right? Now, that doesn't mean that they have to have 2, but it does mean that they could have neither child, right? That's going to be a leaf node again. But they could have a left child, or a right child, or both. Right? And that's what I have over here. Right? What I have over here is what's called a binary tree. Binary because it's limited to 2 children at most. The root node here has both a left child and a right child. The left over here and the right over here. Right? E has no left child, but it does have a right child. Let's see, another one. C has no left child, but it does have a right child. H here, that has a right child, but no left child. Who has a left? There we go. There's I, and they have a left child, but no right child. And then you have others that have no children at all. Those were the aforementioned leaf nodes. Okay? All right. That's our first binary tree. Right? Binary tree. Okay? It doesn't have to be full. Right? We'll talk about what it means to be full here in a second, but we need some more terminology instead. Okay? This is again referred to as a binary tree. Right? So the depth of a node is the length of the unique path from the root to the node. And let me go ahead and give that a name. So the depth of a node U is the length of the unique path from the root to that node U, right? So let's come over here and note what the depth of each one of these is. So let's go ahead and look at the node. I've got a bunch of them, A, B, C, D, E, F, G, et cetera, et cetera. And let's go ahead and look at the depth. I'm going to skip A for a second here and jump immediately to B. If you start at the root and traverse left, you got there at a cost or at a length of 1. So the depth here for B is 1. And because I drew them all on the same level here, you can immediately guess that the depth of C is going to also be 1. Right? So those are all my depth 1 nodes. What about D, E, and F? It would take 1, 2, 1, 2, 1, 2 length paths to get to them, right? So all 3 of these are going to end up being of depth 2. Let's see, G, H, I, J, K, G through K. That's going to have depth 3. Right? L through Q, that's going to have depth 4. What about R down there? That's going to have depth 1, 2, 3, 4, 5. Right? So 5. Now let's go back up. I skipped A for a reason here because it's not immediately apparent what the length of the path is. If you're on A and you need to get to A, do you need to do anything? How much did you walk? 0. So its depth is also 0 there by convention. Okay? So that's the depth. What about the depth of the tree? The depth of this tree is going to be 5. That's because it's the maximal depth of any node here, right? How tall is that tree? It's as tall as its tallest branch, right? And that branch is of 50 feet high or something like that. And so we have the notion of the depth of the tree. The depth of the root node is 0, right? The depth of the tree itself is the maximal depth of any node, right? Okay. So once we've got these definitions, how can we exploit it for a fast data structure, right? What I want you to do is, let's do this thought experiment. What if over here I do not have a full binary tree? What if I did though? What if we had a full binary tree? Every node was present at every level or depth up till the maximum depth of the tree. Let's draw such a tree, okay? I'm going to start with depth 0. And I'm going to note the total number of nodes at that level, right? Well, if I only have 1, then we call that a seed, right? And that's it, right? There's only 1 node, okay? By the way, the depth of that tree is, actually the depth of that tree is going to be 0. You can have an empty tree, right? No nodes at all. The vertex set ends up being the empty set, if you've seen that notation before. And the depth of that ends up being -1 by convention. It's weird. Yeah?
Why would you have an empty tree? For what instance?
You just need empty sets sometime for induction, for completeness. Why do we need 0? Well, if we have 0, we shouldn't even be talking about that thing. No, we need that for an additive identity, right? For math to work, right? All right, so I've got a depth 0 node there. What if I go to the next depth here of depth 1? And both the children are there. Remember, it's a full binary tree. Depth 1, I've got 2 nodes there. What if I continued this? At the next depth, how many nodes will I end up having? 3. I'm not going to, I'll go ahead and draw them all. How many did I end up drawing there at depth 3? 8. Do you start to see a pattern emerge? What if I were at depth k? What would it be? This is a geometric series, so powers of 2, it'd be 2 to the k. Okay? Keep going until you get down to the depth of this tree, right? D. There are going to be 2 to the d nodes at that depth, right? Whatever d might be. Now, what is the sum total of all of these things? Add all of these up. Right? This is going to be a summation of k running from 0 up to d of 2 to the k. Remember that this is just going to be 1 plus 2 plus 4 plus 8 plus 16 plus ... plus 2 to the d. Right? That is not our old friend Gauss there at all. Right? This is a geometric series now. Okay? Does anybody remember the closed form solution from this? Maybe from calculus? No, that's okay. Don't worry about it. There is a general form solution for this for any base, not just base 2, but for base x. Right? And it's something like x minus 1 over x to the blah, 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 or whatever, right? Don't worry about it. It simplifies in the case of 2 to 2 to the d plus 1 minus 1. Right? If you want to verify that really quick, what if I just looked at these first 5 terms here? Right? D would end up being 4. Well, what's 4 plus 1? That's 5. So 2 to the 5th minus 1 is going to be 31. Go ahead and sum up those numbers in your head really quick, and you'll see that it's 31. It's 1 less than the next power of 2. Okay? So now why did I go through this thought experiment here? Right? The reason I did this is because if we can develop an algorithm or a data structure and algorithms to go with it, such that I can insert stuff, retrieve stuff, and delete stuff, the basic CRUD, create, retrieve, update, and destroy, such that all operations are proportional to the depth, and the depth is small, then goal achieved. Remember that we started this whole discussion here on Friday, or on last week on Thursday, by reviewing what we had looked at before already. Linked lists were really, really efficient if you were doing things at one end or the other, right? But they were terrible if you were trying to do something in the middle or an arbitrary index-based stuff, right? Array-based lists, that got flipped around. That if you tried to insert or delete from the start, then that means that you had to shift everything down, right? So order n operations. However, an index-based search was super, super efficient. In fact, if it was sorted, you could further exploit that using binary search to get order log n arbitrary search. We also looked at stacks and queues, but they were only efficient because we limited what you could do with them. You could not do an arbitrary retrieval, insertion, or deletion. You could only do it in a very specific, limited manner, restricted manner. So what we want is a general purpose data structure to achieve all this stuff. And if it's proportional to the depth and the depth is small, then we've achieved our goal. Let's come back over here and review the math. What was n again? It's the number of nodes. Right? D is the depth of the tree. If I can get things to be order D and D is small, then done, right? Again, achieved. Let's go ahead and see what D is here. 2 to the D plus 1 minus 1. Let's go ahead and solve for D here. I'm going to take 1 to the other side. That's simple enough. Is equal to 2 to the D plus 1. Right? So how do I get rid of that 2 right there? Say what? Take a log. Take a log of both sides. Log of n plus 1 is equal to, taking the log base 2 on the other side is d plus 1. Right? So what is d in the end? It's log of n plus 1 minus 1. In other words, it's big O log n, which is super, super fast, right? Because we've already seen binary search. It is an exponential speed up. Hopefully you experienced that on your first assignment too, right? If you used binary search to go searching for missing records, instantaneous. If you use linear search, you were probably going to be there for 20 years or so, right? But this is much, much better. This is fast. Unfortunately, we're not going to get there entirely, but we can start to make progress to get there, okay? So again, a full or nearly full binary tree, excuse me, we haven't talked about search yet, has a guarantee on the depth. Where n is the number of nodes, the depth is going to be logarithmic. If you can perform operations proportional to the depth, then all of your operations will be logarithmic as well. Okay? All right, so what I want to do is I want to take a little bit of a detour here, and let's talk about how you would actually do something like this in practice in Java. So let's go ahead and create a class, right? And I'm going to call this tree node. And I'm going to parameterize it immediately because I remember from when we did this with linked lists and with array-based lists that I had a first version that did not parameterize, and it was only good for integers. Now I'm going to parameterize it because I immediately know I want a binary tree that I can put, you know, strings into it. I can put integers into it. I could put doubles into it, all right? Okay, so what is a tree node exactly? Let's come over here and look at this tree again. If I'm just looking at one of these nodes, obviously I've got the data in there. And the data here is just represented by a single letter. But that's going to be a thing, right? So what is that thing? Well, whatever you're trying to store there. Private, final, T, element. Okay? What else do you need if you are a node? Here, this is a node. It needs a reference to its left child and its right child. Anything else? What else do you see? Yeah, you probably want to go backwards too, right? Or back up to your parent. So 3 references here. This sounds really familiar, right? What if I didn't have a tree? What if I took my tree and then I trimmed it down so that it was just one branch, one sticks coming out of the ground? What would it look like? A, B, C, D. In other words, there are only left children. What is that thing right there? That's a linked list, right? And so it actually kind of makes sense now that it's logarithmic, because what is binary search doing? Binary search is cutting the array in half each and every single time. And if this is a balanced tree, right, I've got roughly half of the elements over here and half of the elements over here. If I can go ahead and cut it in half, then I can search for something over here, I can search for something over here. I've essentially cut it in half each and every single time. We'll see how to do that later on with binary search trees. But it's an improvement over linked lists. The point is, it's an improvement over linked lists in that it has references to 2 things, okay? Not just one. Private tree node, T, the parent, the left child and the right child. Left child and the right child. Right. Those are all tree nodes, just like a linked list. A linked list had the next, maybe even the previous. In this case, though, I have a left child and a right child. Okay? All right? Let's go ahead and add some bells and whistles to this before we move on. What I want to do is I want to, of course, have a constructor. Let's see, source. Let's go ahead and generate a constructor using fields. I'm just going to go ahead and do it only for the element itself here. Right. Why? Because I want to, that's why I made it final up there. I want you to be able to put data in and eventually get it out, but I don't want you to ever change that data. Right? Once it's in there, it's final. It's not going to change. You can change the parent, the left child, and the right child. Why would I want to do that? Because like the linked list, if you want to insert something, what you have to do is you have to make this one point to the new node, and then this new node point to that old one, et cetera, et cetera. So you do want to make changes to the topology or the shape of the tree. And we do call that pruning, right? You prune the tree, or any arborists out there, what is it called when you take a branch of a tree and try to put it onto another tree? It's transplanted grafting, right? You didn't know that you could do this? You could take, this is, in fact, a lot of industrial plants that we think of today would not be reproducible if they died out, right? Because we've grafted them to the point where that's the only way that they reproduce. I think bananas are this way. And so if we just stopped cultivating them, they would be extinct. And we wouldn't have bananas anymore. But that's how new varieties of apples occur, right? They graft branches of one tree onto another tree, right? All right, so we want to allow people to do that too, right, with their data structure. I'm going to go ahead and generate getters and setters here. Select all, generate that. Note here that it's not going to generate a set element because it is final, but I will allow you to get the element. I'll allow you to get the parent, the left child, the right child, and I will also allow you to generate setters here. Let's go ahead and go with all the setters. There. I'll allow you to change who the parent is, who the left child is, and who the right child is. Now there might be some things here that would come in conveniently later on, right? For example, how many children do you have? Public int get num children. All right? So int value, total, I guess total, num children equals 0. And then if they have a left child, if this dot has left child, then also go ahead and increment that. Num children plus plus. Right? If this has a right child, then I'll go ahead and increment that. Right child. And I'll return num children. I did that automatically in my head here using plain old English. Right? If we have a left child, then we'll go ahead and increment the number of children. If we have a right child, we'll increment the number of children. What's the problem though? I don't have that function. But in my head, that seemed like it's such a nice function to have. Let's go ahead and make it. Public Boolean has left child. What's the logic for determining whether or not you have a left child? Initially, what value is this left child going to have? Implicitly here, this dot left child is null. Right? They have no left child. So, return this dot left child is equal to, or not equal to null. Right? That's the logic I want. If it's equal to null, then it does not have a left child. If it is equal to null, or if it is not equal to null, then it has a left child. Same thing for the right. Right. And right child. Okay. All right. What's some other convenience things that I would want? If I'm going to be traversing this tree and going up and down and up and down, right? With a linked list, how did I know that I was at the end? There was no next. How do I know that I'm at the end here? If there are no children, what did we call that thing? A leaf. So let's go ahead and add that too. Public Boolean is leaf. Return this dot get num children equals 0. Right? If they have no children, then they are a leaf. And that way you can know, I can't go down any further in the tree. Right? Get class, get num children. That's what I wanted. There we go. All right. What's the opposite? What's at the top of the tree? Is root. How do you know if you're a root? It's not whether or not you have children. It's whether or not you have a parent. Return this dot parent is equal to null. If your parent is null, then that means that you have no parent and you are the root. Right? There might be some other convenience things here that we would want to put into this class. I would also want to come back and add my documentation here. I probably would have added these later on as I found, there should be a function to determine if this is a leaf so that I don't go any further, right? Well, let's go ahead and go back and implement that. What I want to do now, though, is actually look at what the tree implementation would look like. I'm going to call it binary tree, and I'm going to parameterize it so that you can put whatever you want in this binary tree, strings, doubles, integers, whatever. Private. Should I keep a collection of tree nodes? Did we do that with a linked list? With a linked list, did I keep track of every single node? Nope. That's no different than an array-based list. I'm not going to keep track of every node here either. All right. Should I keep track of every single leaf? I don't see why. Should I keep track of every single internal node? I don't see why. I want to keep track of one of them. From one of them, and that one unique one is the root, from that one, I can get to anywhere else in the tree. I can traverse back up the tree and down another side of the tree if I need to, right? All I need to do is keep track of one node. Right? If you're keeping track of multiple nodes, you don't have a tree anymore. You have a list or a set or something like that. Right? So private tree node of elements of type T, and I'll call it root. That's it. Public binary tree this dot root is equal to null. Another thing that we kept convenient from both of our list implementations was the size of the list. And I'm going to do that here too, because I learned my lesson from designing those. I want to keep track of the size here, just like the others. And initially, it's going to be 0. Now we can go ahead and design the interface, much like we did before, right? I'll go ahead and say public void add element, and we'll take on element here. Right? Ooh, how? I don't know how to add anything yet, right? Public void, remove element, add element, right? Well, could I add element at an index? And could I do that? This doesn't make any sense anymore, because what the heck does an index mean with respect to something that looks like that, all right? So it's not going to be index-based, certainly. I'm just going to go ahead and give it to the tree, and the tree is going to decide how to insert it somehow, right? I don't know how to solve that yet. Right? But what I do want to find out is, or find is maybe public t find element, right? Find element, t element. Now you might be asking yourself, well, wait a second. If you already have the element as input, why are you returning the element if somebody already has it? And that's because this is typically a dummy key, right? So you're searching for a person based on their UUID or something like that. You would create a person object and set only the UUID. You don't have their name, their first name, their last name, right? If you had all that data, then of course you wouldn't even need to store it here because you'd have it already, right? Instead, what you have is a dummy key. An instance of that object where the search parameter is set, UUID, but the rest of the data is not. So I'll go ahead and hand that over, that dummy key over. You give me the full piece of data, the full version of that object. Okay? So you want to do something like this. All right? How am I going to do that over here? Okay? With a linked list, it was pretty darn clear. Right? You had to start at the head of the list. And traverse, that ain't it. Nope. Traverse, that ain't it. Traverse. Oh, there we go. We found it at the end. Right? But what about this tree over here that has two options of which way to go? Right? I want to find the data associated with, say, J. Right? If I'm standing here at the top, right, I don't know if it's that direction or that direction. This is kind of like a maze. Do I take a left turn or do I take a right turn to get out of this maze? Right? If I took a left turn over here, I would, maybe eventually find my way back up here, but without having found J. Okay? And how do I know that I came from that direction so that I never go that direction again? So does anybody know how to solve the blind man's maze? Right? Or the maze where it's complete darkness, right? You do not know how to get through this maze. So, yep, I'm seeing what? The left hand, the left hand trick, right? So you take your left hand, you stick it on a wall, you can't see anything, right? You just keep walking, right? Eventually you will come out of the maze. Why? Because you go down a dead end. Well, guess what? You wrap around back as long as you are consistently doing a left hand. It could be a right hand too. It doesn't matter. As long as you're consistent about it. Don't let go of the wall, right? If you let go of the wall, of course, and then all bets are off, right? You can just find the wall again and then just start over. What does that look like with respect to this tree? If I start at the root and I treat this as a wall, right? I will walk down to that node, walk down to that node, walk down to that node, walk down to that node. That is a dead end, right? So I end up wrapping back up because my left hand is on the wall here. And you start to see the pattern emerge. I'm going to treat this as a perimeter, right? Not as a maze, but as a perimeter here. And eventually, I will come back all the way up here. Right? So if I'm able to walk around this, this tree in this manner, right? Then I'll never forget where I came from, right? And I will not end up exploring. Once I come back up here to A, I still need to find J. Oh, wait, did I go that way direction or did I go that direction? Because I'm walking in this direction. I'm not going to backtrack needlessly and explore the same thing twice. Right? How do we end up doing this with a computer, though? Right? Visually, of course, we can do that trick, right? And we can go ahead and stick our hand in the wall, and we can understand that. Dumb computer can't understand that, right? So what we need to do is we need to develop a more rigorous algorithm to do this. And there are going to be three options here. There's what's called a pre-order traversal, an in-order traversal, and a post-order traversal. All three of these have their own applications. Right? So all three of these are going to be useful in some way. Okay? So let's just look at the very simple tree of 3 nodes. There's the root. Here's the left. And here, it doesn't draw perfect ovals. There we go. And here's the right. Okay? A pre-order traversal processes the root node first. And then it proceeds to go to the left tree second. So 1, 2, and then it does the right node next, right, last. So it goes in a root, left, right manner. That's the ordering. An in-order traversal just changes the order a little bit. Before it processes the root, it says, wait, no, I'm going to go ahead and explore deeper first. Right? I don't know if this is the exit or not, or the piece of data that I'm searching for. I'm going to go ahead and search over here first. So it goes left. Then once it comes back up from that exploration, then it processes the root node. Then it goes down over here to process anything that might be in the right subtree. So it goes in a left, root, right order. And as you can imagine, the pattern holds here for a post-order traversal. I will do the left first, right? Come back up, still wait for the root, go back down to the right and process that second. Once I've come back up, then and only then do I process this last. Yeah?
For an in-order traversal, is the initial direction arbitrary? Does it matter if they go right?
Good question. So 3 things, root, left, right? And 3 things, there are 6 permutations, right? 3 factorial. So you could go root, right, left. You could go right, root, left, right? You could go right, left, and root. And there are the other 3 permutations. We generally don't look at that, though, because who reads right to left? And besides, those are going to end up being the same order of the mirrored tree, right? If you take this, and I don't think I can do it with good notes, but if you take a mirror image of this, in other words, you just take this and move it over here, and you take this and move it over there, right? Then it ends up being the same exact thing. So you could mirror image your tree, and these 3 end up being the same. Right? It's not as useful. Right? Okay? Let's look at a very small example here. A to B, C. We'll put both children here, D and E, and then F hanging off over here. What does a pre-order traversal look like here? Again, we always start at the root node no matter what. Right? Before we go left, before we go right, we process this node. What does process mean? You look at it, you print it out, you have data, right? What does processing your data mean, right? It's abstract, whatever you're trying to do with it, right? So for me, I'm just going to print it out or enumerate it here. I'm just going to list it. So I've processed A here. Now I go left, and then I go right. So when I come down here, I'm looking at this subtree right here. This is the new root, right? From the perspective of the subtree, B is the root here. And so I end up processing B next. And then I process, again, 1, 2, and then 3. So D and E next. Right there. I am now done with this left subtree. I return back up to my parent here. But remember that I've already processed that because I processed the root, then the left, Now I need to do the right. So I come down to this subtree here. My root is now C, and so I will process C. But there's no left child. I would have processed it next had there been a left child or an entire tree hanging off of this thing. But since it's not there, I immediately proceed to the right child. And F is the last thing. One observation here. With a pre-order traversal, where is the root? Always going to be the first one. What about an in-order traversal? I do not process A first. Instead, I go down to the left subtree. Then I will process this, and then I'll process this over here. I come down here, and I'm looking at this subtree, which is B, D, and E, but the order that I process it in is in the in order, so I do not process B, I process the left one first. 1, 2, 3. And so I have D, B, and E. Once I'm done with the left subtree, I come back up here, and I've got A. Why? Because I do the entire left subtree here first, then the root, then the entire right subtree third, right next. Right? I'm down here now. There is no left child, so I end up processing C and then F. Right? Slightly different. Right? Another observation here. Where is the root now? It's right in the middle, right? If you want to call it the middle, right? That just means that everything in the left subtree is over here, everything in the right subtree is over here, and A is right in the middle, right, of both of those. Right? What about a post order? These are all one word, by the way. Pre-order, in order, post order. Not post, space, order. It's one word. Okay? Post order, I do the left subtree first, then the right subtree. Tell me where A is going to end up being at the very last. Right? Okay, so let's process the left subtree next. I do not process B. Instead, I process D, E, and then B. 1, 2, and then 3. So D, E, B. Right? I come back to A, but I do not process it yet because I'm going to process the entire right subtree next. Right? So I process the left, but there's nothing there. Then the right, which is F. And then the root, third, C. And as you guessed or predicted, A is going to end up being at the very last. So A, the root, is always going to be last over there. The root, or it's somewhere in the middle, or it's in the beginning based on a pre-order traversal. Okay? All right. That one was pretty easy because it's on a small one, right? A small tree here. Okay? So let's look at that other tree again from before. This binary tree right here. All right. That's too big. There we go. All right, let's do a pre-order traversal. Pre-order. Right. While I'm doing this, what I'm going to do is I'm going to keep track of where I am. Right. So you remember, not Goldilocks and the Three Bears, Hansel and Gretel. There we go. Hansel and Gretel. In fact, do you remember when we started talking about stacks? Right? I think I mentioned Hansel and Gretel. How did they were led into the forest to be abandoned, but they were able to find their way back, or they hoped to find their way back. How? By leaving little breadcrumbs behind them. Right? If I'm at a particular node here, U, right, I need to know where I came from. Did I come down? Did I come from my parent? Right? Because, and in which case I need to traverse to the left. Or was I done processing the left subtree and somehow I've come back from that left subtree, in which case I need to go down to the right subtree? Or is it the case that I came from my right child and then I need to proceed back to my parent? Right? I need to keep track of all of that stuff. So to keep track of all that stuff, what I'm going to do is I'm going to create a stack. Right? More accurately, the stack is going to keep track of what I still need to do, right? Let's start out up here at A, right? So I'm going to go ahead and keep track of my current node, and I'm going to say that that's A because that's where I start, okay? Now I'm going to look at A's two children here, right? A, B, and C. Right? I'm going to process B next, right? Before I process C. But I do not want to forget that I still need to go to the right tree. I need to remember that C needs to be processed still. So what I'm going to do is I'm going to put it into the stack here, C. And then I'm also going to put B after it. In other words, I'm going to push the right child first and then the left child here. Right? And then I'm going to process A, which simply just means printing it out over here. So let's write out these steps. 1, push the right child if it exists. 2, push the left child, again, if it exists. Right? And then 3, process the node, right? The current node, the current node, okay? There's also another step here to determine. I'm going to go ahead and move all this down here, right? This 0 step. Did I tell you about the basic programming language before? You started out every line number, every line of code was like 10, 20, 30, 40. Why? Because sometimes you'd have to go back, oh, I forgot a step. I now need 15, right? So you always went in increments of 10 and then hope that you never did 10 screw ups or 9 screw ups, I guess, between them, right? So I only need 1 screw up here. Why? Because on the next iteration, what am I going to do? I'm done processing A because I already printed it out. Where do I go next? B. Where is B? It's at the top of the stack. So current will take on the value, whatever my stack is, dot pop. Right? Okay? So let's do that. A goes away, and B here now, I pop it off the top, and there's my current. Right? I repeat this process. Right? I push the right child of B if it exists. I push the left child of B if it exists. What's the right child? E and D. There we go. And then I process, and then fourth step here, process the current node, which is B. And so I don't want to retype it. I'm just going to move it over here. There we go. All right. A, B. All right. What's the next iteration going to look like? I'm going to pop off the next one. Right? I'm going to push the right child, push the left child in that order. Here's D. And so I'm going to push H. I'm going to push G. H and G. At this point, do you see what's in the stack? The things that I still need to process at some point. Right? All right, so process that. Right? Pop off whatever's on the current stack there, G. Push its right child, which is M and L. And once again, here I'll highlight them. Right? Let's do a different color. There we go. These are things that I still need to process, right? I'm going down over here, remembering that, well, okay, you need to process this one, then this one, then this one, then this one, in that reverse order, because a stack is a LIFO data structure, right? Last in, first out. It's breadcrumbs. How did you get to this point? Well, I came down this direction, and I needed to process C, E, H, and M when I get back, C, E, H, and M when I get back. Right? All right, so G, there we go. I'm going to pop off the top here. L comes over here, and I push the left child and the right child. But tell me about the right child of L and the left child of L. Do not exist. When we go to code this, we're going to make a check, right? Is that null? And if it's null, then I don't push it. If it's not null, then I do push it, right? But here with pseudocode, I'm just going to go ahead and write it out like this. I'm not going to write the tedious if exists, if not exists, right? All right, process L next. There we go. Now what do I do? Remember, I'm going to start backtracking now. Now, I'm not explicitly taking a step back. Instead, I'm using my stack to remember, where did you need to go again? Oh yeah, that's right. I'm at M now. I push the the right child, which does not exist, and then I push the left child, which is R. Process M, and it's up there. Push R, and guess what? It has no children. It's a leaf. So we end up processing that without changing anything. At this point, I'm going to go ahead and erase that highlight because I have returned all the way back up to D in effect now, remembering that H is where I need to go next. So pop that off. I push the right child, and the left child does not exist. So that ends up being N, right? Process this. Pop that. It has no children, so end up processing that. And now I've returned all the way back to B, right? Or implicitly here, E. Right? Okay. E gets popped off the top. Right. The right child is I, right? And the left child is non-existent. And so we continue. E, right? I gets popped off, and O is pushed. Right? Nothing gets pushed for the right child, and then O got pushed. Right? There we go. I. O gets popped off, no children, so it ends up getting processed over here. Right? And we're now all the way back to implicitly the top here. Tell me, when are we going to stop? When there's nothing left, how do you know that there's nothing left? The stack becomes empty. Right? All right, so let's continue though. Let's finish this out. Right? C gets popped off the top. I push the right child, which is F. There is no left child. Right? There we go. I'm going to take away all those highlights now. Right? There we go. I'm at F. Right? I pop that off the top. Right? Now it's empty, but I'm in the middle of this loop right here. Right? I just popped this. I need to push the right child and the left child here. So K and J. Right? Then I process F. J gets popped off the top. And by the way, if we were searching for J at this point, we would stop. Right? I found what I'm looking for. I simply just stop and return. Right? Otherwise, J has a right child and a left child, Q and P. Right? And so I process that. Right? And ultimately now I'm not going to push anything else. This is going to come out. There are no children, so it gets processed. This is going to come out. There are no children, so it gets processed. This is going to come out. There are no children, so it gets processed. And now I'm done because the stack is empty. I get to the end of this loop, right, and I'm done. So here's the pseudocode for all that processing, right? My input is going to be a binary tree with root, with a root. So here, I'll just go ahead and do it like this, with .t dot root as its root. Right? And what I'm going to do is I'm going to output a pre-order traversal of T. Okay? My first step is to create a stack here, empty stack. Right? Now to get started, what I'm going to do is I'm going to push onto S the root of T. Right? This dot root, I'm using that indirect component selection operator that started in C, probably started before that. But if I've got T, T's root basically. Right? So this is less pseudocodey because it's very, very much like a C or Java or pretty much any programming language that has a component selected or selection operator. Right? But that's okay. Right? It's so common that we'll just go ahead and use it in our pseudocode. Remember, there are no rules to pseudocode. There are only guidelines. If I gave you rules to pseudocode, you'd have yet another programming language. Right? Now I'm going to go into my while loop here. Right? While S is not empty, right? I will do these parts over here. In fact, I'm going to go ahead and No, I'm not. I won't be lazy. We're going to pop off the current vertex. Current is equal to s dot pop. Right. Then I will s dot push current dot right child. Right. And then s dot push current dot left child. And then I will process current. And once I've broken out of that while loop, that's it. Right? There's no more to process there. Okay? Really quickly here, we're not going to be able to test this today since I don't have a way to get anything into this tree. But let's go ahead and write that. Right? So let's, just so it compiles here, let's go ahead and get rid of that. Let's go ahead and take this pseudocode here and translate it just directly one to one over here to my binary tree implementation. Right? So public, I don't know what the output here will be. In fact, let's just go ahead and make it void for now. Right? And what I'll do is I'll do void pre-order, print pre-order. Right? There we go. And so all I'm going to do when I process something is I'm just going to print the current to the output. Okay? All right. So I'm going to take that first line and create an empty stack. Do you remember in Java what is it? No, it's this week. I guess don't remember in Java unless you did your lab this week already. We covered it in the lecture, but is there a stack in Java? Yeah. I mean, there's another stack interface, but the one that we used was a deck, right? Remember, it's a double-ended queue, right? And it can hold whatever you want, right? Actually, in this case, I'm going to hold a tree node. Right? Because what I was doing over here is I was pushing a node, pushing a left child, pushing a right child, and so it's going to hold my tree nodes. Right? And but I am going to call it a stack, right? New. I think what is it? Linked list? Linked list is a standard implementation of this. So let's go ahead and pull that in. Pull in the deck. And make sure that I've got enough Langle Wrangles there. There we go. So there's my new empty stack. I'm going to push the root. So stack dot push. This dot root. There we go. While stack dot is empty, while it's not empty, right, I'm going to do 4 things. I'm going to pop off the top and process, and eventually process it. So tree node t. I'll call it current here as well. Stack dot pop. There we go. And then I will push its right child and push its left child. So stack dot push. Cur dot get left right child, there we go, and cur dot push left child, excuse me, left and right and left in that order. But be careful. Should I be doing this blindly? What if they don't have a right child? What will I end up getting? Null. I would end up pushing null onto my stack. I don't even recall whether or not the deck allows you to push null values, right? In fact, it does, but I don't know if this method allows you to do it. Right? So I'm going to go ahead and add to my pseudocode, in other words, translate my pseudocode here into a condition. If cur.has right child. Right? Oh man, that came in convenient, didn't it? Right? Then I will push it. If cur.has left child, then I will push it. Only if they have them will I push it. Okay? Otherwise, system.out.println, what is it, cur.getElement. There. Right. Now, again, we're not going to be able to test this because putting together, I have put together this tree before. I just don't have the code here. But let's go ahead and try putting together this tree right here to see if we can get it. Right. So let's go ahead and create some demo code here. Class demo. And I do want a main. Let's go ahead and just create a binary tree. Binary tree T. Let's go ahead and put strings. T is equal to new binary tree. Now what I want to do is I want to create something that looks like that, right? So let's go ahead and create those tree nodes. Tree node, T, A, and I'll just call it A, right? New tree node. I guess same thing, but here A. And this is not a T, this is a string. There we go. A, B, C, D, E, right? F, there we go. A, B, C, D, E, F. B, C, D, E, F. Now what I'm going to do is I'm going to manually create this topology over here. The way that I'm going to do that is by setting a dot set left child to B. A dot set right child to C. Do you see that right there? Okay. All right, and technically I need to set the parent too, but that's okay. I don't need to go all the full 9 there. But I do need to keep track of B dot, actually let me just grab this. B's left child, B's right child. What should I set those to? D and E, respectively. D and, oops. D and E. Let's see, what about D? Do I need to set anything for that? Not its left child or right child. E's left child, right child, no. C, I need to set its left child to null, but that's already default. And so I only need to set its right child to F. F. There. And this should be D. There. Do I have all the necessary relationships? I think. B, C, D, E, F. Okay. Let's output that, print that that pre-order traversal. So T dot print pre-order. Now remember, what does a pre-order traversal look like here? A, B, D, E, C, F. What? Stop. Play. There we go. Ah, darn it. Tree node has right child because cur is null. Okay. I did screw up somewhere. Where? How did null get on the stack? Oh, did I never set the root? Oh, I never set the root. So T dot root is equal to A. That's what it was, an empty tree, right? Now, unfortunately, I'm not going to be able to do that, right? But let's go ahead and modify this just a little bit to make this package protected. So I'll go ahead and make this into like that. It's not exactly public, and this is not the solution we want. Eventually, we want to implement this, so we don't have to worry about that, right? But I am able now over here set it as the root. In fact, let's talk about design a little bit. Public void set root to be tree node T new root. This dot root is equal to the new root. There we go. Does that sound like a good design right there? What have I done? I've exposed the fact that there are tree nodes inside this thing. Ultimately, what I want to do is I want you to be able to add stuff, remove stuff, CRUD, create, retrieve, update, and destroy, right? Without regard for how this stuff is being stored, right? Yes, it's called a binary tree, but I could have just as easily have called it a sorted list, right? Or something, right? Like you're going to be doing in assignment 7. You don't have to do binary trees, by the way, binary search trees, because we're not there yet. But in any case, let's go ahead and try this now. Remember, it should be A, B, D, E, C, F. A, B, D, F, E, C. Oops, did I screw up? Uh-oh. B, C, oh, B, C, D, E, left, right. Right child for F, and then print pre-order. Did I screw it up over here? A, B, D, E, C, F. Nope, this is correct. A, B, D, E, C, F. All right, there's something screwed up right here. All right, let's go back to, anybody see what it is?
I don't think D should have a right child.
Oh, wait. D should not have a right child?
Yeah.
Oh, you're right. What the heck? That should be C. Duh. Okay, I screwed up on my setup there. All right, A, B, D, E, C, F. Oh, hey, it worked. Thank you. A while ago, I set up this one much larger here, and so it'll come out to be correct on Thursday when we do that one instead. All right, you got to be careful here because an in-order traversal and a post-order traversal is not as simple as these 4 steps. Right? You can do it with a stack-based, but you're going to have to keep track of way more information. Like I said before, if you're at a node U, right, then you need to keep track of where you've been. Right? If this is my current, right, then here's my parent. Here's my left child, left, and here's my right child. Doesn't have to look pretty, okay? You have to know, did I come from my parent or did I come from my left child? Let's undo that one. Did I come from my left child or did I come back up from my right child? Okay. So if you came from, let me move all this over to give myself some more room here. If you came from the parent, the left child, or the right child, right, go to, right, how do I keep track of where I go to next? Well, if I came from my parent, where do I go next? Down to the left child, right? So left, right? If I came back from my left child, where do I need to go to next? Down to my right child, so right. If I came back from my right child, I need to go back up to my parent to continue exploring, right? So go back up to the parent. And process, and process if, and only if, ... All right, let's figure this out. If I came from my parent, right, this first situation, I'm eventually going to go to my left child. But if this is a pre-order traversal, before I do that, I need to process that pre-order. Right. Now, what about an in-order traversal? If you're coming back from your left child, before you go down to your right child, you process it, but only if this is an in-order traversal. Right? And finally, if you're coming back from your right child, then that means that you've processed your left child, you've processed the right child. Now, at the end, a post-order traversal order and process the current if and only if one of these 3 things. Right? All you need to do is keep track of, all you need to do is keep track of where you've been. That tells you where you're going. And depending on whichever pre-order, in-order, or post-order traversal you're going to use, then that means that you'd process it then. Right? Now, it looks simple. It's deceptively simple. But the number of corner cases that you have to figure out, right, and null pointer checks and stuff like that, it's actually quite large. Right? The pseudocode is quite large in the book. So we won't actually implement those that way. We'll implement them a different way. Right? In fact, here's the preview of how to implement this. Right? So think of recursively, U. Right? I need to process U. Right? That's one thing that I need to do. Right? What else do I need to do? I need to pre-order traversal and use left child. Right? I need to also pre-order traversal and use right child. The way that I wrote this is what? recursive. Right? If you have, if your input here is the current node, right, then go ahead and process that because it's a pre-order traversal. Then you can go ahead and recurse on the left side and recurse on the right side respectively. Right? We can do that in like 2 seconds here. Let me go ahead and give you a pre-order traversal instead. Right? That is recursive. Pre-order recursive. Right? And here, let me go ahead and give 2, and this will be the private version. Private, and it takes a tree node T current. Right? And so what I'm going to do here is I'm going to call this function over here, but to get it kicked off, I'm going to go ahead and pass in this dot root. Right? Okay? Now what is this going to look like? I do not need a stack anymore. Right? All I need to do is these 3 things that I said over here. Process the node, invoke this recursive call on the left child, invoke it on the right child. So system.out.println current.getElement. Right. Then pre-order traversal on current.getLeftChild and pre-order traversal on current's right child. Now, if this is going to be recursive, you need your base case. How do you know that you've fallen off the edge of this tree? This tree right here. Right? You're coming down. Okay, process R, that's checked. That's done. If I go to the left child, that's going to end up being null. So let's check for that. If current is equal to null, then simply return. There's nothing to print. Let's run this version instead, over here in the demo. I will get the exact same output, but it's all recursive. Now, you might immediately be saying, well, okay, which one's better? How many people vote for the recursive version here? This is the one time where I would say that recursion kind of makes a case for itself because look at that simple code. It's just 3 lines, right? There's no thought process in that whatsoever, right? Oh man, that one's like a dozen lines of code and a smart data structure, right? So, which one's better? How many people like the recursive version first more? No? You do? Okay, for simplicity. What about this up here? 1, 2, okay. Why? Smart data structures. Right? Smart data structures and dumb code are a lot better than the other way around. I'm kind of convinced of this because it's so simple, right? But still, you're abusing the call stack, right? If I gave you a tree of depth, of a huge amount of, huge depth, right? Mine is going to work. That one's not going to work. Why? Because of Stack Overflow. Right? Which one is more performant? Probably this one. I'd want to. It depends. A linked list, yeah, a linked list implementation is probably going to be okay. Right? I don't know. We'd have to test it like a million times anyway. Right? But anyway, you can do a pre-order, in-order, and post-order, all recursive as well. What would it look like? How would it look different? When do I process the node? Do I process it before I make those recursive calls, between them, or after they're all done? We'll look at that on Thursday. Thursday, right? Yeah, Thursday. Okay. All right. See you up in lab.